Okay guys, good morning. So today we are going to talk about how we graph an absolute value equation. So first we need to, kind of recall what absolute value is, right? So absolute value is the distance of a number from 0 on the number line, right? So for example, we can say that the absolute value of 4, right, and those bars here represent my absolute value notation is 4. And we can also say the absolute value of negative 4 is 4, because 4 is 4 units away from 0 on the number line, and negative 4 is 4 units away. So informally, we say the absolute value is always positive, which is true, as long as there's no negative outside the symbol. We're going to talk about what the graphs are going to look like. Part of the graph is going to look like something we've seen, right? A linear equation, but it's going to be strange in the sense that it's going to be V-shaped. Not U-shaped like a parabola, but it's going to be V-shaped, as we'll see. So we're going to do what we call our kind of baseline benchmark case, which is absolute value of x. Now, we can change the appearance of the graph slightly by introducing coefficients, fractional coefficients, negative coefficients, putting things outside the absolute value. But this is our benchmark. So when we refer to different graphs, we compare them to this graph. So we're going to go all the way back to when we were graphing using a table. And we would use -2, -1, 0, 1, and 2. And we want the absolute value of x, right? So the absolute value of -2 is +2. The absolute value of -1 is +1. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. So regardless of whether x is positive or negative, we realize the y values will always be positive. Okay, so when we graph it, we're going to have -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Now, if we decided to extend those values, we could do that, and it would look like this. So when we graph it, we're going to have an arrow here, and we're going to have an arrow here, and we're going to label just like we normally would. We can also do this using the graphing calculator. So if you go to the graphing calculator, you'll go to your y= screen like we normally would, and I can show this to you guys in class at some point. You go to your y= screen, and on the top, you would hit math, right? The math button is below the alpha button, and then you have these 4 headings: math, number, CPX, and PRB. You go over one to the right to where the heading says NUM, and the first one down is ABS. So again, if you wanted the calculator to do this, you would go to y=, telling the calculator you want to input an equation. You'd press the math button, and you'd scroll one over to the right. So on the top, it's going to say math, and next to that, it's going to say MUM, right? That's where we want to be. We want to scroll over to MUM, and then the first one down is going to say ABS. That's the absolute value symbol. Now, when you press that, it's going to give you the open bars with the cursor in between. So what you do is, in between, you would press the variable button, right? The X button, which is to the right of alpha. And again, that's something you could experiment with, and we can talk about in class. But that's what our graph is going to look like. It's going to be V-shaped, right? And in this case, all the values are going to be above the x-axis because the absolute value of the quantity has to be positive or 0. So it wouldn't make sense to have any negative y values for this particular graph. All right, absolute value of 3x. So I'm going to do the same thing, right? -2, -1, 0, 1, and 2. So 3x, if x is -2, 3x is -6. The absolute value is +6. 3 times -1 is -3. The absolute value is +3. And we end up with the same thing here. So I realize I'm going a little bit fast, okay, because I want to try to make the videos less time-consuming than some of them have been in the past. Obviously, you have the option to pause, so you can slow it down. So this is what my values are going to look like. Again, feel free to experiment with the graphing calculator. So really, what do we have, right? So I'm going to label this. So if you think about it, we've got a little piece here, right? This is basically the line, if you think about it, y = 3x. And then this is kind of like the line y equals negative 3x in the sense that this piece on the right has a slope of 3 and the one on the left has a slope of negative 3. Okay? Now let's take a look at what happens here. Changing the coefficient to 3 made the graph what we call narrower. So when we're talking about graphs of absolute value functions, quadratic functions, which are parabolas, we talk about them becoming wider or narrower, right? Wider means, and I'm doing it with my hands, obviously you can't see me, it's going to be more like this, and we'll see that shortly. Narrower means it's going to be like this. So we can think about narrower being kind of skinnier and wider being sort of fatter. So by making the coefficient of x bigger than 1, we made the graph narrower. All right? Now what's going to happen here? It's going to look exactly the same as the last one, right? Because what's going to happen? All right, and I'm not going to make the actual graph. So negative 3 times negative 2 is 6. Absolute value is 6. Absolute value of negative 3 times 1 is negative 3. Absolute value is 3. So let's go back, guys. I don't need to do this again. It's the exact same table. So we're saying, is it not possible to make this negative then, right? So we've got all these values here. Everything so far has been above the x-axis. Whether I do 3x or negative 3x, it is the exact same graph. Now let's talk about what happens if we introduce a fractional coefficient. So if you think back to when we did this the first time with linear equations, it was the second day, we had fractional coefficients. We want to use multiples of the denominator, which in this case means we're using even numbers. So half of negative 4 is negative 2, the absolute value of which is 2. Half of negative 2 is negative 1, the absolute value is 1, and so on. So my graph is going to look like this. Which, again, should kind of make sense as it ties pretty tightly to linear equations, right? So this is the graph y equals absolute value of half x. And again, this little piece over here is kind of like the equation of y equals 1/2 x. And this little piece here is like y equals negative 1/2 x. Since absolute value is positive, regardless of x is positive or negative, so what did we notice? Changing the coefficient to half made the graph wider, right? It made it flatter because the slope is closer to 0. So if the slope is closer to 0, the line's going to look, each of the parts is going to be closer to being flat. All right, so the question that I normally ask in class, which these questions get a little silly remotely, is what happens, how would we make something negative, right? Everything we've seen so far has been positive. How would we make it negative? And eventually someone says, well, if we put a negative anywhere outside the absolute value symbol, it will make, instead of everything being positive, since the absolute value piece is going to be positive, we can negate it and make it negative. And I say, of course, that's correct. So we're going to start with our same values. So the absolute value of negative 2 is positive 2, multiplied by negative 2 is negative 4. The absolute value of negative 1 is positive 1, multiplied by negative 2 is negative 2. Negative 2 times 0 is 0. Negative 2 times 1 is negative 2, and then negative 4. So pretty much if this is going to be the opposite of absolute value of 2x. So again, the only way we're going to really, at least for today, tomorrow's lesson is going to go a little bit further. But in these basic cases here where there's no addition or subtraction, the only way we're really going to get something to be negative or below the axis is if we drop a negative sign outside. So bringing a negative number outside the value made the graph open downward, right? I know we like to say things like it made it upside down. True. Compared to the original, if y equals absolute value of x is our baseline, right, our benchmark we call it, our standard, then putting a negative outside is going to take that and make it upside down in the same way that if you remember when we did parabolas, negative x squared made our parabola upside down, right? Technically, though, we said the language they use in the Regents is opens downwards. So instead of opening upward, as in getting wider as we go up, it's going to open downward. And that's only going to happen when we've got a negative outside here. So this is our classwork, right? So this is what we're going to do in our notebooks. Okay, we can go over it the next time we're in class. We can talk about how we can graph these situations. Our next lesson is going to be an extension on this. It's going to be how do we translate. So in other words, all we did was change coefficients today, right? What if we have something like this? What if we have something like this? Those are going to be very, very different cases. And to some extent, one of them is going to be the opposite of what we expect. So a little preview of what we're going to do for tomorrow's lesson there. But again, this is going to be your classwork. Your homework is on Google Classroom, right? So this is going to be your classwork. So you can do this all on the same graph. And then when we watch tomorrow's video, we'll learn how we can translate absolute values using addition and subtraction.